Hi everyone, welcome to the second NetSeminar of the year. Today we have Arpit Gupta, who is a second year at Georgia Tech. He's working with the Teamster and also advised by Jennifer Rexford about insights. And so without ado, he's going to talk about STX today.
Thanks, Lisa, for the introduction. So I'm going to talk about STX, which is basically software-defined internet exchange point. And let me start with the definition there. So in recent years, what we observed that with the advent of this video content getting so much of significance, what happened was that big giant content providers like Akamai, Netflix, Google, they tried to have peering relations with as many networks as possible and at as many locations as possible. And the result of that was that we had like more interconnected and flat internet. And this flat internet actually requires a set of peering arrangements and fine-grained traffic control. So even though this inter-domain ecosystem is and was evolving, but the underlying routing protocol, BGP, is actually not. And with BGP, we are still making routing decisions based on destination IP prefixes. So it's very hard to make path selection based on, say, source IP address or nature of application or, say, time of day. And with BGP, we can only influence your immediate neighbors, right? So it's very hard to affect or influence path selection at some remote location. And it's not that BGP does not provide any kind of mechanisms to control routing, but these mechanisms are kind of indirect in nature and usually unpredictable. So there is a very indirect control over the data plane forwarding with BGP. So we tried to answer that, how can we overcome these limitations of BGP? And the answer was like, why don't we use SDN? Why don't we consider SDN for inter-domain routing? Because SDN is actually known to make routing decisions based on multiple header fields. So you're not limited to just the destination IP prefixes. You can use different other header fields to make path selection decisions. And then it also provides you with the ability to control the entire network with single software programs. So your impact, your influence is not just limited to your immediate neighbors like BGP. And unlike the indirect mechanisms provided by BGP, SDN actually provides direct control over the data plane. So you can have more flexible control over the data traffic. You can put direct control over the data plane traffic rather than as compared to the BGP. So we all understand that, okay, SDN for inter-domain routing is a good solution. SDN as a solution is actually awesome. But we're talking about BGP here, and BGP is something which is being used by more than 50,000 networks around the globe, and there are like billions of dollars of investment already in place. So proposing a solution and saying that let's replace everything BGP with SDN is kind of not seen. So we had to come up with some solution, an approach in which we can incrementally deploy SDN for inter-domain routing. And for that, we thought about, why don't we start this deployment thing, start deploying SDN at the Internet Exchange Points. And why Internet Exchange Points? Because they provide you with a leverage that even if you make an SDN deployment at one exchange point, it's going to yield benefit to hundreds of participants that are present at those exchange points and probably the neighbors of those participants, right? And these exchange points currently are the innovation hotbed because they're at the front line of peering tussle going on between the content providers, the eyeballs, and other different kind of players of the internet ecosystem. So they themselves have a strong motivation to innovate. And there are a lot of solutions are talked about, like what different kind of solutions are possible with the exchange point itself. And third is that there is a significant growth in the number of exchange points which are being installed in recent years. So it's not just big exchange points which are important, it's also those small exchange points in remote corners of the world which are understanding, which are realizing the importance of exchange points. So there are more and more exchange points are being deployed all over the globe. So before I talk about like what STX is, let me give you a brief background about like what a conventional exchange point looks like. So the typical conventional exchange point, what we have is we have a layer 2 switching fabric. There are multiple participants, different autonomous network, autonomous systems in place. So we have A, B, and C different kind of networks in, which basically connect at this exchange point, they exchange the BGP routes, and they also exchange the traffic with each other. And as the number of participants at the exchange point historically grew, so they realized that they cannot have one-on-one BGP sessions with each other, so they came up with something called route servers. So they basically have peering sessions with one, like all the participants route server, and then route server basically assists exchange of BGP routes. So this was for the scalability purpose. Now, with respect to this conventional model of exchange points, what we propose is that let's replace this switching fabric with SDN switch, right? And let's subsume the behavior or functionalities of the route server, and now let's call it STX controller. And this STX controller is not only assisting exchange of BGP routes, but it is also taking these SDN policies of different participants and combining them. It opens up new kind of possibilities, right? So these new kind of possibilities are because like we can have more flexible business relationships. Now the participants at the exchange point can have peering arrangements based on all these kind of are and flexible. So you can have like more fine-grained traffic engineering, like inbound and outbound traffic engineering policies defined at the exchange point. And thirdly, it enables better security because it enables these participants to prefer routes which are more secure and remotely or locally block rules of the traffic which is creating, like bringing attack traffic to their network. And I have a laundry list of applications which are possible with STX. So STX enables these applications which are either very hard or impossible to implement in current networks. So some of these applications are like, as I mentioned about dropping of attack traffic. If there is an attack traffic which I observe that this attack is being generated from this guy, I can write block rules at different exchange points and make sure that this traffic does not reach my network, or in fact, it does not even bother other networks too. Then there is about inbound traffic engineering, that you can divide the traffic which is coming to your network based on the nature of application or like what kind of peering relationship you have with other guys, right? So you can have much finer granularity of inbound traffic engineering in place. Then you also have this application-specific peering, in which you make peering decisions based on different parameters. For example, like volume of traffic, the time of day, and all those things. So you can have like video traffic peering arrangement with Comcast, and then you have non-video peering arrangement with AT&T. Then there is about server load balancing, that we can offload this functionality which we are using DNS for, that decide like which request should be routed to which data center. That can be offloaded to the STX itself, and you can make much finer grain, like you can make redirection decisions at a much finer level of granularity. And another thing is about the redirection through middle boxes. So there were some proposals in which you can offload the functionality of middle boxes from the networks and put it in the cloud. So STX can actually enable that you can make a much fine level of granularity decisions that like which traffic should be forwarded to which kind of middle box in the cloud. So this is just a list of applications which are being possible with STX. You can find more details about them in the paper, but I will discuss two of them in a bit more detail here. So one is the dropping of attack traffic. So we have this scenario in which we have AS, A, B, and C, and there is an attacker from ASA who is attacking the guy who is in ASC, right? And traditional blackholing approaches in which what you can do is that you can reject whatever traffic is coming from ASA and then protect your network. But with STX, what you can also do is that you can write some drop rules at different exchange points and make sure that this attack traffic is blocked right in the middle of the internet. Right? So if I try to compare this approach with the traditional blackholing, so there are three important points to note here. One is that you have remote influence, that you need not be physically present at these exchange points to block this traffic, but these decisions, these block rules can be put at the exchange point remotely also. Second is you can be more specific about who's attacking your network, right? So you need not block entire, because currently the routing decisions based on destination IP preferences, right? So if you're blocking something, you're blocking the entire IP address space. But now you can be more specific that who the attacker is, like where this attack is coming from, which application this attack is for, and then write drop rules according to that. And thirdly, you can have a much more coordinated effort in blocking this kind of traffic, because it's not just, you're not influencing this kind of decisions that the traffic which is coming to your network, you are putting it in the middle of the internet, so you can put these block rules at multiple exchange points and block for different, you can also protect other networks.
So I don't understand the first one, remote, like remote influence, physical connectivity to STX not required. I mean, who are these remote people who are not going to have a, I mean, don't you at least, I mean, isn't it the same with BGP that, you know, you don't have to be physically present there, you can do things remotely. All that's required is a business relationship between you and the person who's installing either the BGP rules in one case or the SDN rules in another case. So the BGP behavior or the SDN behavior.
So I think the kind of abstraction which we provide in STX is not limited to the physical participants. You actually do have a remote participation at the STXs. And you can write rules for the traffic which is coming to your network at the exchange point. So it's not, you don't need a business relationship with other guys, you need a peering arrangement, or you basically need some arrangement with the STX itself, and so that it works.
So you're saying that before I'd have to have a relationship with Google, but this time I can have a relationship with the STX. But there has to be some relationship between Google and the STX with Google for Google to say, oh, it's okay or not okay to block traffic from my network. Because Google might get unhappy if Yahoo says, oh, I just want to block all traffic from Google because I'm getting a DOS attack from Google App Engine or something.
Right. So this is a very subtle issue, but like what our hypothesis is that like you have to define who's the owner of the traffic in this case, right? And in this case, like what we have hypothesized in this scenario is that whoever is receiving the traffic can have a say that what traffic should be received or should not be received. So if it's AT&T who's receiving a traffic from Google and there is some guy who's like there is some DOS attack probable from the Google, then AT&T can say that, okay, this traffic is coming to my network. I'm not physically present at STX, but I want to write these rules which block this traffic, which I suppose is attacking traffic, right? So this is like AT&T's traffic, and AT&T can express those kind of policies. So this is what remote participation is.
I think the subtle thing is that if you really do need both a business relationship and a technical mechanism, you know, between and sort of political agreement as well between the participants in order for this to work. And also, if you look at, just to say one more thing, so some of Nick Feimster's previous work was using BGP to do a sort of SDN to see, how far to, basically produce an API to BGP that allowed you to sort of program it. And, it seems like you could do the same things with that. The advantage here is that the SDN rules are more fine-grained, and you don't have to sort of, put the square BGP into the round hole of what you're trying to do.
Right. So I'll just add here that like whatever we do with STX it's mostly the case that you could have done this with other approaches too, but it's about simplicity, right? Like it's about the ease. So you can do it with this case.
So just one question. If you're receiving the traffic, why? I mean, do you really care to do it 3 ways, or do you just care that it isn't consuming?
Paying a link, and then this track traffic is coming by the transit link. So I might want to, I will be happy if I can save that. But more than that, it's like rather than having some complex mechanisms like firewall kind of mechanisms at my own network, I can have these rules deployed at the STX, and it can protect me from these kind of attacks.
But as long as it's done at the other end of Madhya in the EIX teams, it's fine.
Yeah. So moving ahead, there's another example I want to discuss. It's inbound traffic engineering. So you want to basically divide the traffic which you're receiving. You want to make a choice at how you're receiving traffic for the prefixes you are advised. Let's consider a simple scenario here. We have 3 networks, A, B, and C. Like all 3 of them are connected to an exchange point. And AFC has 2 routers at the exchange point. It is advertising a prefix, and it wants to control that what traffic, like how it is receiving the traffic for this prefix. So let's consider a scenario in which like it has provisioned resources for the HTTP traffic, which are much closer to C1, the router connected to C1. So it wants to have a policy in which it says that whatever traffic is coming to my network for destination port 80 should be received or should be forwarded to port C1, right? So the question is, can you do this with BGP? And the answer is no, you cannot have these kind of fine-grained policies with BGP. But can you do this with STX? And yes, you can easily do this with STX. Why? Because STX uses SDN, and SDN gives you direct control over the data plane forwarding, and you can have these kind of fine-grained policies at these.
But can you do that with MPLS though? Or?
Sorry, what?
Can you not do that with MPLS?
It's so I don't have.
Yeah, but I mean
that's what people are using today, right?
Right. It's again the same thing. I mean, like you can do that with STX. It's with MPLS, but it's much.
No, I understand that. I mean, just the
right.
something.
Yeah, I'd say MPLS is probably what people might be using.
I mean, we understand that.
They can also use, I mean, I think it's worth considering the alternatives. I mean, you
It's
could
not
also,
so much that you're using MPLS, it's just that you're doing DPI to steer the traffic into an LSP.
No, I mean, what SDN brings into the picture in terms of traffic engineering is that the dynamic nature, that you can change things on the fly, you can
I mean,
apply
MPLS
policies
with
and
a,
respond to that. I mean,
MPLS with a sort of convenient dynamic API could basically do this, but most of the time MPLS uses sort of different a different and more complicated control plane.
Right.
okay.
So these are just few examples, but what this gives an idea is that STX is enabling applications which are either impossible or very hard to implement in current networks, and it is trying to solve the problems that you were initially talking about, that inter-domain ecosystem is evolving, but the inter-domain routing is not. But STX is not just about putting SDN switches at the exchange point. Building an STX which is real, it's deployable, is very challenging. And I'll talk about those challenges here. The first challenge is the programming abstraction itself. And imagine that we're talking about exchange point where we have multiple autonomous systems are connecting. All of them have to express policies which cater to their business interests. So we have to provide them independence. We have to provide them privacy of their policies. But at the same time, because all of it, so those policies actually have to be combined together. And we have to think about how we're going to resolve those conflicts. So the question we have to actually answer is that what kind of programming abstraction we should provide to these participants so that they can express their policies independently, they will have their privacy of policies, and at the same time we can combine those policies together and resolve the conflicts. Second challenge was interoperation with BGP, because since this is an incrementally deployable solution, so we are providing these flexibilities of SDN at the exchange point, but everybody else is using BGP. So we have to make sure that this cost of flexibility is not coming at the, benefit of flexibility is not coming at the cost of correctness of BGP. So we are not creating any kind of black holes or loops in the network with SDN and STX in place. And second is about scalability. So imagine a scenario in which you want to write complex traffic engineering policies with matches on hundreds of thousands of IP prefixes and also on multiple header fields for one single network. And the number of flow rules, number of policies you'll see is huge. But then consider that we have to write these policies for hundreds of participants at the STX, and then we have to combine all those policies together so that we have one coherent switch behavior. And this is a big, big scalability challenge. So I'll talk about all these points in a bit more detail and start with the programming abstractions. And the question here is that how are these participants going to express their policies? So one simple or very naive idea which we came up with was, okay, let's let these participants directly program the STX switch. And the problem here is that if A says that whatever is port 80 traffic, let's drop it, and C says that whatever is port 80 traffic forward to C1, then there's a conflict because STX does not know that for port 80 traffic whether it should drop the traffic or whether it should forward to C1. But after a closer inspection to this problem, we realized that we're trying to solve the problem in the wrong way, because participants' policies need not be applied to all the traffic that is coming to the exchange point. Rather, it should be restricted to the traffic which it is either sending or receiving, right? So the research challenge or the question we had to answer was that how can we restrict participants' policies only to the traffic that it sends or receives, right? So for that, we actually came up with virtual switch abstraction. And virtual switch abstraction, because we all love virtualization. So what we did was that we provided each participant with their own virtual STX. So everybody has an illusion that they are the sole programmer of their own virtual STX switch, and they express their policies. Each of them express their policies for their virtual. And these virtual switches interconnect with each other according to the pairing policies they have. So in this case, like A, B, and C are all interconnected with each other. So there is an interconnection between the virtual switches. And the way we solve, so this basically ensures that there is all of these participants can express policies independently, and nobody, AST is not going to look what policies are expressed for virtual switch of ASA. So there is a privacy of the policies too. And at the same time, we are trying to solve this problem of conflict by following the natural order in which packet traverses the exchange point. So let me illustrate that with a simple example. So we have case here that ASA expresses a policy that maps destination port 80 forward to C. And that's for the virtual switch of ASA. Then for virtual switch of ASC, there's a policy that if it's destination port 80, forward to C. So we have a packet coming in, and that's destination port 80, right? And because it is received, it is coming from A's network, so it will go to virtual switch of AS. And then we will apply whatever policies are expressed for virtual switch of ASA, which says that, okay, if it's at port 80 traffic, then forward to C. So this packet goes to virtual switch of ASC. And now we have the policies of virtual switch of ASC, which says that if it's at port 80 traffic, then it should be forwarded to C1. So it comes out by port C1. So notice here that the policies applied on each packet is basically determined by the natural order in which the packet is traversing at this stage. And this is the approach which we took to resolve the conflicts, because we are now not, like, we are first letting all these participants to express the policies independently, and then we are coming up with this kind of scheme in which we are figuring out, like, how are we going to combine all these policies together, resolving the conflict. So this is the first part of the challenge. Second part was the interoperation with BGP, and the interoperation with BGP is an important challenge. Why? Because at the STX, what we are providing is that we are providing that you can have very fine-grained, flexible policies, but at the same time, you are also trying to go in an incremental deployable manner, making sure that everybody else talks in the same way they were talking previously, that is BGP. So we are providing flexibility. What we want to make sure that this flexibility is not coming at the cost of any correctness issues with the BGP. So we don't want to break BGP itself. We don't want to create any forwarding loops. We don't want to create any kind of black holes. So there are a lot of subtle issues which we have to resolve. I will focus on one of them. And the requirement here is that like forwarding decisions at the STX should only be along the BGP advertised routes. So what prefix? It's more or less like a permission that I am advertising this prefix to you, so you can send traffic to me for this prefix, right? And if I'm not advertising a particular prefix to you, you should not be sending that traffic to me. And at STX, we need to make sure that this permission model of BGP is respected. Otherwise, we will be creating forwarding loops in which, like, there will be advertisement, but there will be no advertisement, but there will be traffic sent. So let's consider this scenario. We have ABC again, and B and C are advertising set of prefixes. And A's policy is that if the traffic is like match destination port 80, then it should be forwarded to C, right? But now consider there's a packet coming in, whose destination IP is 20.1 and destination port is 80, and it's coming via A. So if I naively apply A's policy, this packet will actually be forwarded to C. But C never advertised the prefix 20.1. So like we have to, like in STX, we have to ensure that this packet P is not forwarded to C, right? And what's the solution? The solution is a simple policy augmentation. So what we have to take into consideration is that before we have any kind of policy which say forward to particular participant B or C in this case, so we have to make sure that what are the prefixes advertised, and we have to augment the policies before forwarding decisions. So in this case, like destination IP advertised was 10/8, so we have to put a match on destination IP 10/8 before forwarding them. Right?
But the timescales at which they're being updated are very, very different. Right? The BGP route tables are changing every second if the policies are done.
Right. I'll come to that. But yeah, that's a very good point. I mean, like you have to take into consideration that these policies, if you're matching on IP prefixes, then you have to take into consideration that whenever BGP updates comes in which changes this, then your policy set should also change. Right?
I mean, you don't know that. I mean, if somebody could be doing very fine-grained load balancing, which could have to be much faster than once a second. And in that case, it would make it worse by adding in the first part of the policy rather than the second.
But if you're manually updating the policies and you're competing with BGP route updates that are
Right. But the point is that this is SDN, so it's you probably have an API to update the policies, and there's probably software that's doing it.
So then you need a policy to update the policies.
But even if you have to update the policies, I mean, like given the scale at which we are operating, a single BGP update without any optimizations in place, it can screw up the entire system.
It gets worse if you consider that you've got this explosion of all basically sort of end-to-end mappings going through this, right?
So so that's a good discussion we're having here, because this should actually also give you an idea that when we're talking about scalability, right, we're talking about rules which are matching on destination IP prefixes, right? Because like you have to augment the policies which match on destination IP prefixes. Then you have rules which match on multiple header fields. And that's just for one participant, but ultimately you have to combine all the policies together and then push them down as a set of flow rules which the STX switch can understand. So scalability is actually a very, very big challenge for STX. But I can divide the scalability challenges into two parts. And first part is that we have to reduce the data plane state itself. Like when we're talking about these so many matches, then we are talking about so many open flow rules, right? And those flow rules, like there are only n number of rules which can be supported in the switches which we have. Like even though we have the most advanced high-tech switches in place, but still there is a limit on that. And we call this problem as a fib explosion, and it's a very serious problem when we're talking about STX because there are too many flow rules in place. And second is the control plane computation, that we have to reduce the control plane computation because it's like one, that when you're putting things up, then it will take a lot of time. There are so many participants policies. When you compile those policies together, it will take time. And second is like when there are BGP updates coming in, then you have to recompile the policies. And then that can also take time. And if it's like taking an order of a few minutes, it's going to be a fruitless system. So we kind of emulated, when we started this implementation, we tried to evaluate, get a rough idea that, okay, if we have 300 participants policies, some representative 300 participants at the exchange point, and some representative set of policies, then it was actually taking the number of flow rules which we were talking about were on the order of few minutes. And the amount of time it was taking to compile all those policies together was of the order of few hours. And this was a serious roadblock because like you cannot build a system which takes, for one BGP update, it takes 2 hours to complete, right? And there are always BGP updates at the exchange. So let's focus on the first problem, that we have to reduce the data plane state. And for that, we actually came up with two observations. One is that these internet routing policies are actually not defined for individual IP prefixes. They're usually defined for set of prefixes, right? So it will be a huge waste of flow space or time if we are writing and expressing policies for individual prefixes. So we should think of some approach in which we can get rid of that. Second is that edge routers of the participants who are connected at the STX, they are actually already matching on prefixes and assigning some next hop to those prefixes. So that functionality is already there. So we thought about like, okay, these are the two observations. Let's try to combine all these things together. Can we write rules for groups of prefixes, and can we somehow use the computational power of these edge routers? So first thing which we did was like, let's figure out what are the prefixes which have the same forwarding behavior. So what we did was like we tried to analyze all the policies which are expressed by different participants, and we were able to figure out like what are the prefixes which have the same forwarding behavior. And second thing which we did was that we played around with this BGP's route server itself, so that rather than advertising actual physical BGP next hops, we were advertising virtual next hops to these participants. And we were advertising one virtual next hop for one group of prefixes. So in this simple example, in which 10/8 and 40/8, these are the prefixes which have the same forwarding behavior, and then we have 20/8, which is a different forwarding behavior. So we assign, say, red BGP next hop for that and yellow one for the other one. So what this signifies, or what this results in, is that rather than having rules for individual prefixes, now we can have rules for these BGP next hops, and these BGP next hops or the virtual next hops are representative of all set of prefixes, right? Because whenever the traffic is coming for, say, 10/8, 40/8, it will be sent to the STX with a virtual next hop, right? And then rather than writing rules for these prefixes, individual prefixes, we are writing rules for BGP next hops. And remember, initially I was talking about when we did this initial analysis, and it was taking the number of flow rules we were talking about was the order of few millions. We were actually able to bring down up to like around 300, we considered 300 participants at the exchange point, some representative set of policies, and from few millions we were able to bring that down to less than 35,000. And talking about the control plane computation, so those control plane computations can be divided into first half is initial policy compilation. So in initial policy compilation, we actually leverage the domain-specific knowledge of the policies. That okay, these policies, if they're not applied on the same flow space, they should not be composed in parallel, or all those kind of different optimizations in place. We also leverage this memoization in the compiler itself, and we were able to bring down this compilation time from few hours to less than 15 minutes. The second important point is the policy recompilation, right? So there are two ways in which policies can change. One is when the participants decide that they have to change the policies manually, or there are some automatic scripts which are changing the policies based on volume of traffic and other parameters. But the most important is that when you're talking about these exchange points, and there are always BGP updates coming in. And when BGP updates coming in and you have policies defined for prefixes announced by a particular participant, then those policies might change. So what we did here is that we did two things. First, corner out or isolate the set of prefixes, with a set of policies or set of rules which will get impacted with a particular BGP update, right? And second, we made an observation that these BGP updates are actually coming in bursts. So we can push down rules which are non-optimal in terms of size, but are correct in terms of forwarding behavior, right? And when there is a period of lull, then we can figure out what's the optimal state of the flow rules down in the STX switch. So what we like with these optimizations in place, we were able to come out with results in which most of the recompilation, whenever BGP update is coming in, were completed within 100 milliseconds. So we were able to actually implement all these solutions, all these optimizations in the platform. And we have the STX platform, which is complete with the BGP integration too. And we have to kind of test beds to test and evaluate different kind of new and novel applications with STX. So one uses transit portal, and second actually uses Mininet. So in Mininet, what we did was we leveraged this the container behavior in which we were able to actually mount the file space too, and then we were able to emulate the router behavior in the Mininet nodes. So that actually emulates the router behavior. Then STX at the switches can also be emulated in the Mininet. So we have an entire topology with say 100, 200 participant exchange point, which can be emulated, and all the behavior performance things can be done. So you can have a deeper look in what our platform is about, and all the details are there. We have some demos and experiments which you can run and try out with STX. And as a matter of fact, we also created an assignment based on STX, and more than 900 students are actually able to follow those instructions and complete the basic configuration of the STX. So that kind of works. So I'll talk a bit more about the test bed here, because it's kind of important to understand that whatever applications that you were talking about, do they actually work, right? So I'll focus on this application-specific peering application, in which you want to control or you want to have peering relationship based on the nature of traffic, right? We have three participants again, A, B, and C, and they are connected at the STX switching fabric, and they are actually getting the real traffic to the STX switching fabric by the transit portal. So what transit portal does is that it advertises the prefixes, it brings the real traffic to the switching fabric, which we have in our lab in Gupta. And the policy here is being expressed by AS of C, and the policy is simple, which we were exploring in previous slides too. That if it's destination A port 80, if it's a match destination port 80, then traffic should be forwarded to B, right? So let's look at the results here. So for initial 10 minutes, and I actually forgot to mention that basically, well, A and B are both advertising the same set of prefixes. So ASC, default choice of BGP route is basically ASA, right? So for first 10 minutes, we don't have any application-specific peering routing policies. So we have 3 UDP flows starting, and each of them have an output of 1 Mbps. So we see 3 Mbps of output, which is for ASA. And we start the policy application-specific peering policy at around 10 minutes. And then what we see is that one flow, which is port 80 flow, it goes via ASP, and other flow is following the default traffic. And then around 20 minutes, what we do is that we withdraw this traffic, we withdraw this prefix, and then we see the same state going back. So this kind of demonstrates that if you have some kind of application which you can try out. So this is one example which we have with the transit portal testbed, but we have some more use cases and applications in the GitHub repo of ours, which you can do with Mininet itself. So let me briefly talk about the current state of STX deployment. So STX has gained some attention, and we have a lot of projects going on regarding the deployment with Internet 2, Ginny, and SOCKS. And there are some use cases which have been thrown to us by ESNet and NSA that they want to have exchange point with some specific use cases in place. And so this is specific to research and education networks, but we are also in touch with some commercial networks, especially as I mentioned that there is an exponential growth in setting up exchange points in remote regions of the world. So we are in touch with Internet Society and getting in touch with some of the new exchange points which are being established in US, Eastern Europe, and Africa. There is also an NSF program to actually encourage STX deployment, especially like multi-site STX deployment. So in future, we will see more of the STX deployment which will be coming from different researchers. So what's the next step here? And talking about the problems, like going back to the original problem, that we want to make the inter-domain routing more flexible. We want to make sure that the inter-domain routing is in sync with the evolution of the inter-domain ecosystem itself. So the ultimate goal which we have is like we should have an STX mediated internet. And I'll walk you through the timeline of things. So currently what we have considered is that we just considered a single deployment of STX, right? So whatever problems, challenges which we have talked about are about like when we have one exchange point in place. And next thing which we are currently working on is multi-site STX, in which you will have STX deployed at multiple locations. And the abstraction provided to the participants are that it's like one big switch, and there will be a different end-to-end peering paradigm for all the participants. They will be directly, like they will have an illusion that they're directly connected to the other participants, different places. And if we like, so I guess we are currently at this stage, and what we are exploring are the use cases which will actually demonstrate that this kind of idea of STX mediated internet makes more sense. And we believe that we have some of the use cases in place which will motivate this scenario. But assuming that we are able to complete this, then the next step is that, okay, we'll have this deployment in a more intense manner and try to replace the BGP completely. So I'll talk a bit more about like replacing BGP, but like it is more about division, about how people interconnect with each other. So it's about having layering structure in the internet itself, so that like all the networks connected to some instance of the STX, and then STX takes care about how traffic goes on between the exchanges, and you basically will not need BGP in that case. So when I talk about STX mediated internet, it has advantages, right? Because we're talking about new endpoint peering paradigms, so that you can have more flexible policies at the exchange point. Those will be tailored to the traffic which is exchanged at the exchange points. And the interconnectivity between STX, right? So whatever the traffic is to be carried between the exchange points, that's like we'll have a simple, scalable, and policy neutral spine. And spine is basically interconnection between the exchange points. So you have the traffic between those spines is like STX to STX. It's only like only bits, just carry the bits, and then there has to be a policy kind of schemes in place. And we are also like this proposal which you're putting is not totally disruptive. It's not. It's currently in sync with the current internet ecosystem. We still have the content providers. We still have the eyeballs. We still have the transit providers. So it's not disruptive in that sense. But it also opens up new set of research challenges, right? Because when I'm talking about new endpoint peering paradigm, so we have to think about what kind of policies we're talking about. When you give the possibility that a new guy starts a new network and then he connects in STX and then he's instantly connected to all the networks around the globe, irrespective of the geographical location. So what kind of policies can we explain, and then how are we going to deal with the scalability of those policies? So those are the research challenges. I don't know the answers, but these are the challenges which we have. And when we're talking about policy-free routing between the exchange points, then what kind of routing mechanisms will work? I don't know. There have been some solutions which we can take inspiration from, especially for the wide area networks, but I don't think at this point of time anybody knows that what exactly those routing mechanisms will be. And secondly is that, okay, we have these current players of the ecosystem, but when you have this kind of peering paradigms, and can you have different new kind of players in the internet itself, right? So can you have, because when you have this kind of STX in place, STX mediated internet in place, then you're basically bringing down the threshold of participation of like reaching out to global eyeballs, then you can have different new kind of players. So I'll try to summarize this talk. And what we started with was that, okay, inter-domain routing is not in sync with inter-domain ecosystem, so we should come up with solutions, and we came up with a solution that is a STN-based exchange point. It is promising for fixing some of the internet routing problems. We realized that building an STX is not just about putting SDN switches at the exchange point. It has various research challenges. We solved some of them, but to end this talk, I'll just say that definitely there were challenges, but I don't think we have solved all of them. And there are a lot of open research challenges, both in building a better STX, but also in way you can use the STX. So I'll end my talk here. Thank you.
So I guess, go ahead, yes, please.
So did you look into extending any of the existing BGP mechanisms like BGP flow spec to achieve the same effect as what you're trying to do here?
So I think BGP, so basically BGP flow spec will allow you to have routing decisions based on multiple header fields, right? But at the same time, it kind of requires you, like other participants also, to have BGP flow spec, right? So for example, if you want to have like inbound traffic engineering, and you want to have fine-grained policy about getting the traffic at a based on like application type of application kind of thing, right? Then you need your neighbors also to follow the BGP spec. But in this case, like most of the policies which we are trying to explain, it's more about data plane control. So you can write policies for your network, for traffic which is coming through your network. It does not require other participants to also, like other networks to also participate at the exchange.
But the SDX operates between those two nodes, right? One node is saying, I want you to filter traffic for port 80. The other node that actually ensures that the filtering happens. So that's both of them need to talk the same language.
You can still have policies based. So I'm not, I'm like, as from the beginning I was saying, like this is not something which is like most of the things which you're doing are kind of possible in the current network too. But then there is a different set of threshold for doing those things, and what STX is enabling is bringing down that threshold of participation.
Well, the sort of interesting thing is you know, nobody needs to change their existing BGP to plug into an SDX.
No.
Like they can just plug into it today,
right,
and then incrementally, you know, decide to take advantage of some of the functionality provided by the SDX.
Right. So that's
sort of a nice feature, I think.
Right. This was one of our design principles, and that we want incremental deployability so that we don't require anybody to change whatever their current existing setup is. You just plug and play, come to the STX exchange route with the route server, and you're done. And you don't need other participants also to actually have some STX policy in place.
So I guess one of the benefits of doing something like that is also for network analytics.
Right.
I mean, maybe you have better tools to do those things. But my question, and it's not my question, but I'm assuming that some people, in terms of security, like as a malicious user that hacks into that, STM controller, how do you defend against things like that? And it's not my question, but I'm sure that people have asked
No.
many times, right?
Yeah.
So,
I'm glad you asked this question. I mean, like
because BGP has something like authentication thing.
Right. I'll start with this note first.
And by the way, we're not your PhD committee, so you can make mistakes.
I'll start this note with one thing. Like, okay, our first goal in building STX was to come up with a platform which actually enables things, right? So security was not the first priority, or was not the first consideration which we were having, that okay, this system should be secure. We came up with the virtual switch abstraction, which in a way provides some privacy to the policies that we have. But if there are some specific, like if somebody hijacks the STX itself, so currently there are no mechanisms to ensure that like the policies or the flow rules will not be manipulated. Mm-hmm. But I'm sure this STX platform opens up opens up a new challenge, that okay, now we have this platform in place. How can we make sure that because there is a central dependency here, right? Like everything is basically dependent on STX as the central guy. Right. So I think the next solution, I don't have the solution right now, but the next solution should be in the direction that how can you make sure that it's not so much centrally dependent.
Right. Because you had all these SDX around the world, and obviously, so going back to somebody else's questions. Okay, going back to that switch fabric that you had with the virtual switches. Can you go back to that slide? Yeah. Just for me to understand. So the switch fabric there is not. Yeah. So okay, so this it's a physical switch fabric you assume here, or what do you assume? I didn't get that.
Okay, so this is a virtual switch. I mean, like, this is more of an illusion. It's not a physical switch. So we have just one physical switch in place, right?
Okay.
Yeah.
So those virtual switches are running on what? Is it like an open vSwitch essentially, or
no, it's
like
it's a programming abstraction. It's not even a OBS kind of abstraction. It's a programming abstraction. We provide, so the way it's more about how participants are allowed to express the policies.
Express their policies for. I mean, it's written at the bottom, right? Each guest writes policies for a virtual switch. I was kind of interested in the topology here.
But how do you define those virtual switches? That's my question.
They're created by the. I mean, I'm not sure what you mean defined.
Flows that you install in the actual physical switch make it behave as if it were has their own virtual switch.
Exactly. So that was good. Yeah.
Right.
Yeah, but I mean,
it's the same. Yeah. I mean, it's just like.
But that's not the definition of virtual switch, right? It's not the definition of virtual.
I mean, I will say that the term is kind of overloaded, but yeah.
Unless you're assuming something like if you use like a flow visor type of.
Well, it's more like VLANs, right? That if you imagine that everyone VLANs virtualize a traditional Ethernet bridge. This is using SDN to virtualize an OpenFlow switch, and it's really the same thing. It's like OpenVertex in the SDN world, except that it's not actually trying to virtualize the IP space. It's instead trying to virtualize just the control plane, and so that everybody can specify policies that from their point of view, and then they're merged into the specific policies that are globally correct for everybody.
That's right.
So my question here is this. I'm confused by this diagram, and I also sort of wonder about the sort of connection between sort of policy and mechanism here, which is is this the topology that people see, or do people? And you had this interesting example where you said, well, ASA can forward just to ASC, but he can't pick which of the egress ports to ASC that he gets. And I'm like, well, that's interesting because he might want to pick those ports, but then C might want to pick those ports too. And so that's kind of an interesting political or policy decision. And so is the decision that you came up with, your recommendation for SDX, that basically that's the level of abstraction, which is that if I'm Google, I can direct my traffic to Yahoo, but Yahoo controls which of the which of the ports it gets to.
Unless Yahoo allows Google to define that.
Which they might. I mean,
basically, you can use
so I think,
out of the 5 you can use those 2. So
that's conditional upon the kind of agreements between the two parties. But the abstraction which we propose is like when A is defining his policy, he should not be bothered about what kind of ports C has, right? So it can just say forward to C, and then C will decide which port it wants to receive.
The other thing that I thought, this is sort of, the question, the topology is interesting too. Like, it sort of looks like we've made this ring topology, but really it's a mesh.
Right. This is really a superset of all the topologies that would be seen. Right? Any one port would only see leaf nodes one hop away. So you don't actually have loops in the topology.
Yeah, okay.
I was gonna, well, actually.
On that subject, but back to your question. But if I want to use a low-cost route, right, and I'm C needs to know that, right? So maybe the ASS, they write their own policies for them, but you may want to be aware of somebody else's policies, right? So, see what I'm saying?
So I think let me clarify with the topology question. I guess the first part of it was that there's always one hop thing. I mean, every other participant. So if because A at the exchange point has pairing session with B and C, that's why we have interconnection between the virtual switches, right? So I guess that kind of answers your question. That this is a simplistic topology which we have in place because we just have 3 participants. If we have more, then we'll have more of a mash kind of thing. So now can you say your question again?
Yeah, my question is that in the case of I mean, you can allow C to use whatever port, but if A has a policy that I'd like to have a low-cost, routing, for instance, maybe C needs to be aware of that, right, and then apply, the right thing. So that's why it might be useful, to expose that. So
I think there's just sort of more this general idea of enabling people to make decisions based on other metrics, such as cost, such as available bandwidth, such as latency or delay. And I guess the question is, can you add this into the framework because it'd be really useful?
Right. So I think it basically depends on the kind of applications, as you pointed out, the kind of applications you have. But I think it's also a trade-off between the kind of information you want to expose and then kind of balance you want to create about the clarity of the abstraction. Because one concern which other participants will also have is that about the privacy of the policies too, right? I mean, like they don't want to expose that how many ports I have.
Oh, absolutely. Oh, yeah, absolutely. Yeah.
So if those two participants have some agreement between them that okay, like I will expose these number of ports you have, and you can make a decision about like based on traffic or cost or whatever metric you have. So can we have that? Can I make my forwarding decision based on that? So I think that's a trade-off. Currently, we are not supporting that, but I guess that's easily possible in our.
I mean, one thing that would be really nice would be that we can't easily do today across domains in the internet is get sort of guaranteed bandwidth or latency, right? And so STX, the global STX, hopefully your goal I think eventually should be able to say I can, if I want a certain type of to enable this to happen where it can't easily happen today because RSVP doesn't really work across domains. Right?
So I think there was a research proposal on this work, like not from a group from ETS Zurich. I think they presented it on us also, and they're currently working in this direction. And their goal is exactly what you're saying, that ensure some kind of quality of service when you're connecting at one exchange point, another exchange point. So at least between these exchange points, you can guarantee some bandwidth and the delay guarantee.
Sorry, go ahead.
I have a two-part question. I was wondering what the impact of an outage of STX is. And second, if you were to compare the cost of, compare a highly available STX versus a BGP model, a BGP has a model for handling failures today, how much state would you have to replicate?
Right. I think that's a very fair question. Like even if I forget anything about STX, there is currently route server and exchange points in place. And let's try to answer like, do they have any kind of fail-safe mechanism in place? And the answer is yes, they do have. So like currently route servers, when you connect to route servers, there are like always two replicas of route servers, and then they always maintain the same state. I think currently we are not focused on that, but that's the same model we should need to follow because there is a centrality in place, and like if STX fails, then everything else fails, right?
Right. But policies would still have to be replicated.
Right. So. I don't think that's going to be very challenging task to maintain like synchronization between the two states and like take one as a backup kind of thing. So, but I think that needs to be evaluated. Like currently we don't have that system, so I can't comment on how efficient that will be. But I think that's definitely a need, and that's a model which route servers are already following. So we should like when we're going with the practical deployable STX, then we should be following that.
Any question?
Might be a bit vague, but are there any limitations with the existing hardware that allows you to program the flow tables that would limit you from deploying this in a internet exchange point, like things like packet per second rate or reliability? Like I assume they're nothing like a carrier grade router, I guess, which are traditional.
I would say like flow table size for non-exact match rules. I mean, common hardware has will give you 128,000 exact match rules, but a much smaller number of wildcard rules. And we have crappy hardware, so that would be my question. It's like, is there hardware that can run this?
So I think we have not tested in terms of hardware like replicate the exact exchange point, the volume of traffic, and the rules. So far our evaluation has more been on like, okay, whether like what are the number of rules that will be required, like what's the consistency of the rules. That evaluation still has to be done. And we are in touch with multiple number of vendors. They find STX as a very interesting use case. It's as a testimony of like what consistency or what kind of challenges at the extreme can be solved. So I guess there is an interest. There is a work going on. I think this is still a work in progress. Like the consistency of the data frame is still a work in progress. So in future there will be definitely solutions in that. But I guess the requirements of STX is the in terms of scalability is extreme test for SDN in general, right? I mean, like the kind of challenges which we faced while developing STX were first of its nature. I mean, like the scalability, especially the scalability challenges which we observed. Like forget the data plane, even at the control plane, the challenges which we observed were for the first time. So that's more of like the maximum scale at which the SDN can be tested, the consistency and all those issues can be tested. So I think that still has to be seen. There is a work going on. There are a lot of vendors which are interested in testing out STX and coming out with solutions to the problems, especially in the data plane.
Yeah, I just think it's it's something that was, to me, sort of glaringly missing from the talk. Was like, okay, like I get the abstractions; those are very important. But if you seem to be assuming you could walk into an internet exchange point with the switches we have today and then deploy it.
So
that's the thing that I think is a little bit shady.
So like I think our current target is both ways. I mean, like we're not just targeting the large exchange point; we are also targeting the small exchange point, where the scale of challenges are to a scale, like to a limit not so scary. So I mean, but there are like large exchange points, especially I will point out to M6. They already have the replica of the open flow switches in place, like the exact replica of the exchange point they have for the open flow switches too. So there is a lot of testing going on, not exactly with us, but they are also planning something on the same scale. So I think there is a testing going on, there's an effort going on. But I agree. I mean, like I didn't pointed that out upfront, but that's an important concern.
But one thing that wasn't really clear from the talk, to me at least, or maybe it was implied, but it's maybe not obvious, is sort of how this works from sort of what the technical interfaces are in it, and in particular, like what peers with what over BGP, and also what the APIs are and interfaces are between the participants and the systems. And I think the answer is it's a sort of star topology where every participant is a BGP peer with the STX controller. But maybe not. I mean, that's just my guess because you didn't specifically say that. And then the second, I don't actually know, you didn't talk about, so I'd be interested in if you could tell us a little bit about.
Right, I can talk a bit more about it. So it's not an implicit requirement that all participants should peer with each other. So even if you're
say not with each other, they have to have BGP sessions with the STX controller.
Right. So even if you have the that's a requirement. Like if you want these functionalities of the STX, those BGP routes are to be known by the STX controller, and that's why you have to have BGP sessions with each other. But still, you have the flexibility of choosing not to have peering sessions with others. I mean, like you have peering sessions with STX controller, that does not necessarily that you have to advertise your routes to all other participants of the STX controller. So you have the choice. You have the filtering rules which you can deploy, you can implement at the STX controller or the route server per se. So that flexibility is there. Second question, I guess, was regarding the interfaces and APIs. So I think currently the interface is a bit in a rudimentary stage, I'll say. But the approach is that participants basically express their policies. Currently, we are using Pyretic as the language for this STX. So they express their policies in Pyretic, and those Pyretic policies are transported to STX controller as JSON messages. So then you just pass the JSON message and figure out like what are the participants' policy. You have this mechanism in place, and participants have the flexibility to change the policy. Then it will read again what if the participant's policy has changed, and then recompile the policy. That's the current state. I mean, like there's a development effort going on. Like there are different places in which we're trying to optimize. One is like I mentioned 35,000 rows, but we just considered one physical switch. But in reality, like STX physically also has multiple set of switches in place. So we are thinking about how we can optimize rule placement, like which rule should be placed in this switch so that they have minimum number of rules. And then this is like interface which we provide to the participants is another segment.
I guess another thing is the control sort of in-band through the STX switch, or is there a separate control network?
It's a separate control network.
So all the so if I'm Google and I want to plug in, does that mean I have to have two connections to the STX, one for the control traffic and one for the data traffic, or do they share the same uplink?
That's a good question. I think we have not considered that in detail, but what I imagine is that STX itself, like most of the exchange points, they themselves have some transit providers for them, which basically advertises their individual prefixes to other guys. So that is how I believe the connectivity between the exchange points and everybody who's removed from a different exchange point has to happen. So maybe they will.
Maybe for security reasons also.
Yes, I think it makes sense to have a separate control channel, but it need not be this necessarily be a different thing, but it's about STX prefixes, right? STX has some prefix which others have to reach, right? So it depends on how STX chooses to do that. Like they will definitely need a transit provider to make sure that their prefixes are known to others.
Any other questions? Okay, let's thank Arpit again.
Thank you.